Let's talk about the basics of gravity here. So let's say that we have some mass here, we'll call it capital M, and some mass here, we'll call it lowercase m, and their distance r apart here. So some books call this d, some call it r, whatever. So what Newton found out through his study of the falling apple, so to speak, and the falling moon is what he really studied, is that there is a force of gravity between all masses in the universe. How you find that force of gravity is you take the gravitational constant times mass 1 times mass 2 divide by the distance between their centers squared. This universal gravitational constant is on your constant sheet. It's an incredibly small number, 6.67 times 10 to the negative 11th. And that is why you don't normally notice the force of gravity. If this is like even something big like a pickup truck and a pickup truck, this is to the negative 11th. So your force would still be an incredibly tiny force there. It's only when one of these masses is like the mass of a planet do you start to finally feel that and overcome that to the negative 11th number there. So this equation is on your equation sheet. One of the big ways they ask about this, not too often, and I shouldn't say never, but not too often do they ever have you calculate an actual number here. They seem to prefer proportional reasoning type questions. So let's say this. Let's get a different situation. Let's call the force of gravity between these two F. What will it be over here? Here we tripled the mass of this big planet, we doubled the mass of the small object, and we quadrupled the distance between them. So to do proportional reasoning, remember that we ignore all constants. So we won't worry about big G here in this case. So the force of gravity would be proportional to mass 1 times mass 2 over their distances squared. So now plug in what you did to each mass and distance. So we made one mass 3 times bigger, we made the other mass 2 times bigger, and we made the distance here 4 times bigger. Don't forget to square that distance there though. So when we start to solve for that, 3 times 2 is 6, and 4 squared is 16. So can you see it? So you get 6/16 of the force, or reduce that 3/8. So if we called this force F, then the force here would be 3/8 of that force. Very much tied to this is this new concept of a gravitational field. So we imagine that all mass, there's this thing called a field around us, and the field tells us how the forces behave. These arrows here, these green arrows, represent forces. All you need to do is put a mass there and they'll experience a force. How much force? That's what the gravitational field tells you. It's actually G from before, so 9.8 here on Earth, approximately 10. But now we're going to think of it in a different way. Rather than an acceleration, 10 meters per second each second, we're going to think of it as the force per mass. So how many newtons of force do we get per kilogram? So here on Earth, we get about 10 newtons of force for every kilogram of mass we have. 2 kilograms of mass then, and you'll get 20 newtons of force. So often they'll ask questions again with proportional reasoning with an equation like this. So what you actually do then, this version isn't super useful, but if we take all of Newton's universal law of gravity and we plug it into the top part, let's say that this is the small mass, same as this one like the apple, then that mass will cancel out, and what you will be left with is this. This is the more useful form. The gravitational field strength around any planet, or again, it's also the gravitational acceleration, is equal to G times the mass of the planet divided by the radius of the planet squared. This is assuming, by the way, that you are sitting on the planet's surface right there. Again, they love proportional reasoning questions with these. So let's say that you have a planet and it's got twice the mass of Earth and 3 times the radius of Earth. So what we will use is proportional reasoning with this equation right here. Don't worry about the G, it's a constant. It doesn't affect the proportional reasoning. So it's just mass over radius squared. So how would we handle this one? Like this. We plug in what we did to the mass, we doubled the mass there. And then we plug in what we did to the radius, we tripled the radius, but don't forget to square it. So that winds up being 2/9. This planet would have 2/9 the acceleration here on Earth. So around 2, a little bit more than that. One more thing they love to throw in this chapter, I shouldn't say they love to throw in, it's the only place they throw it in, is where density comes up in this unit. So density is defined as the mass per volume. This is bigger when you do problems with floating objects in AP Physics 2, but here's how it might come up in AP Physics 1. Let's say we got a planet of radius r and density rho there. Let's say you go to another planet and it's made out of the same material. It also has density rho. It's got radius 2r there. How will this affect the gravitational acceleration on the planet? So again, we're looking at this issue right here. The gravitational acceleration will be g times the mass of the planet over the radius squared. Well, let's work with this. If density is mass per volume, then mass is density times volume there. And so, well, let's figure out what happens to the volume. The density is the same, so that won't change at all in this example. So now our mass is just going to be proportional to volume. And the volume of a sphere is 4/3 pi r cubed. So that means whatever we do to the radius, we do the cube of that to the mass. So now we can actually replace mass with the cube of the radius. Again, that's only if we don't change the density. So now we're basically doing this. Let's come back to this equation right here. We don't have to worry about g, because that's always a constant. I'm replacing mass right here and right here with the cube of the radius. And we always divide by the square of the radius. So that radius squared will cancel with 2 of the radii up there, and you'll get the gravity is proportional to the radius. So if we keep the density the same, double the radius will actually mean double the acceleration due to gravity. There's no reason you have to keep density the same. We could have made this a little bit harder and changed the density and the radius. And then you'd have to put, let's say, double the density here and still cube the radius there. And so you might have to worry about that. All right, enough with the gravitational fields. Let's look at one last type of problem. Let's again say that we've got a planet here, and let's say this is a moon, a satellite going around that planet. So this satellite is going in a circle. So it's got a centripetal force on it. It must point towards the center of the circle that it's traveling in. When we go to set up our Newton's second law, like we do with all of our problems, we've got this. The force of gravity is the only thing pointing towards the center, so it's the centripetal force. So we can say that it's equal to our mv squared over r. So plug in the entirety of Newton's universal law of gravitation right here. G times little m, that's the satellite, times big M, that's the planet, over the radius squared. Over on this side, notice we have the mass of the satellite as well, and we also have a radius here. So that radii will cancel out with one of those, that mass will cancel out with one of those masses, and the most common thing they ask you to solve for is the velocity. Once you've canceled out both your masses in this radius and one of those radii, if you solve for velocity, you'll get this, that the velocity of a satellite is the square root of the universal gravitational constant times the mass of the planet divided by the distance you are from its center there. So more massive planet, you'll have to go faster to stay in orbit. Bigger radius, you can go slower. If you have too big of a velocity, then you will go out into a bigger orbit then. If you have too small of a velocity, gravity will win and you'll be pulled into a smaller orbit. Don't forget also that this velocity is also true. This is true the entire chapter. Anything going in a circle, its velocity is its distance over its time. Well, let's say we go around once, then the distance is the circumference, 2 pi r. And the time to go around once is defined as the period. So these two velocities are both true at the same time. So sometimes they might ask you for a problem solving the velocity with the mass and the radius of the planet, and sometimes they might give you information about the period, and then you would solve the velocity that way. Often you use these two to solve for the period of a satellite. And so that works out like this. If I rearrange these equations and solve it for period, it would be the square root of 4 pi squared, you could pull those out as a 2 pi if you want it, times radius cubed over big G divided by m there. So that is the main things for this unit on gravitational forces there.